In today's explainer, we're doing something pretty exciting. If you're gearing up for the BSNL exam, or honestly, if you're just totally fascinated by the invisible architecture that runs our modern world, well, you are in exactly the right place. Our goal today, we're going to take that absolute mountain of a telecommunications syllabus and we're going to break it down into a logical, super easy to remember stack. Because here's the crucial question, right? Have you ever actually stopped to think about what connects a basic old school voice call to the blazing fast 5G networks we literally rely on every single day? I mean, it's not magic. It's this beautifully complex, layered series of technologies. And today, we're connecting those dense exam theories directly to the everyday telecom infrastructure that's buzzing all around you. All right, let's take a quick look at our roadmap. We are building this layer by layer. We'll start with signals and modulation basics, then move right into multiplexing to see how we combine that data. After that, we'll hit transmission mediums and networks, and finally, top the whole thing off with spectrum management essentials. So let's jump right in. Section 1, Signals and Modulation Basics. This is literally the foundation of all telecommunications. Okay, so before we can even think about 5G, we really have to understand that every single piece of data starts its life as a basic electrical signal. And getting that signal ready for its big journey, that process is called modulation. Think of it like packing a suitcase for a very specific trip. Now, historically, we used analog modulation. Think of your classic AM and FM radio broadcasts using a single carrier. But today, we've upgraded to digital modulation. It's incredibly versatile, utilizing both single and multi-carrier formats to pack in way more data. Let's do a rapid-fire breakdown of some key acronyms that are absolutely guaranteed to pop up on your exams. First up, PCM, or Pulse Code Modulation. Honestly, you can think of PCM as the ultimate translator. It's the vital bridge connecting the analog and digital worlds. It takes a continuous, wavy analog signal and converts it into crisp, discrete digital bits. Without PCM, modern networks just couldn't transmit data flawlessly. Next on the list is ASK, or Amplitude Shifting Keying. The absolutely crucial word to remember here is digital. This is definitely not your grandfather's AM radio. ASK is specifically a digital modulation technique. It takes those digital ones and zeros and encodes them by actually shifting the amplitude, or the height, of the carrier wave. And to wrap up our modulation acronyms, we have QAM, Quadrature Amplitude Modulation. Guys, QAM is an absolute powerhouse. It brilliantly, and I mean brilliantly, combines both amplitude modulation and phase modulation. This double teaming effect is exactly what allows for the incredibly efficient, high-density data transmission that our modern internet absolutely demands. Moving right along to Section 2, Multiplexing, or as I like to call it, sharing the highway. So our data is modulated and ready to go. But how do we send it without needing a literally separate wire for every single user on Earth? Well, we share the highway. One primary way we do this is with TDM, or time division multiplexing. Imagine the network is essentially taking turns. It transmits digital signals by assigning these unique microscopic time slots to each data source. You'll see this used all the time in connection-oriented circuit-switched systems like ISDN and PSTN. All right, time for a quick mental math break, because this exact calculation shows up on exams all the time. Say a TDM link transmits 4,000 frames per second, right? And let's say each slot contains 8 bits. What's the transmission rate? It's super simple. You just multiply those 4,000 frames by the 8 bits, and boom, you get a 32,000 bits per second, or 32 kbps transmission rate. Easy as that. But, TDM isn't the only way to share the road. Let's compare FDM and WDM. FDM, or frequency division multiplexing, relies heavily on analog signals. It divides them up using different high-frequency carrier bands so they don't crash into each other. On the flip side, WDM, wavelength division multiplexing, absolutely rules the optical fiber world. Instead of radio frequencies, it separates data streams using completely different wavelengths, essentially different colors of laser light. Okay, layer 3, section 3, transmission mediums. We are looking at the actual physical and wireless paths now. We've packed our data, but what exactly is carrying these multiplexed signals across the globe? Let's look at the heavy hitters. First, optical fibers. These are made of a super low-loss silica glass core, and they use this gorgeous physics principle called total internal reflection to push massive amounts of bandwidth. Then on the wireless side, we've got 4G, which relies on high-speed OFDMA technology. And 5G? Well, 5G taps into extremely high frequencies to unlock those mind-bending, next-gen data speeds we all love. But wait, what happens when you're in the middle of nowhere and you can't just lay down a fiber optic cable or pop up a 5G tower? That is exactly where VSAT saves the day. VSAT stands for Very Small Aperture Terminal. If you're a networking nerd, you already know this is the absolute backbone of remote satellite communication. For anyone in an isolated geographical area, that little VSAT dish is literally their lifeline to the global network. Now, heading back into the city, we have the BTS, the Base Transceiver Station. We're unpacking this one because you absolutely need to know that the BTS is the actual physical mobile cell tower you drive past every single day. These units are the unsung heroes of wireless networks. And because of the nature of microwave communication, they really rely on clear, direct line of sight to function at their best. And finally, we've made it to the top layer, Section 4, Spectrum Management Essentials, governing the airwaves. This is the most abstract layer of our telecommunications stack, but it's arguably the most important. To prevent millions of invisible signals from just collapsing into pure static, we rely on 3 core spectrum management functions. Let's walk through them. First, there's spectrum sharing. Think of this like a traffic cop. It coordinates access to prevent collisions, especially in those wild, unlicensed bands. Then, spectrum mobility. Say a primary user needs a band right now. Mobility vacates it and smoothly shuffles the secondary users to another frequency. And third, spectrum analysis. That's the meticulous, ongoing process of matching specific band characteristics to what the user actually requires. But look, governing the airwaves isn't just setting rules and sitting back. It is incredibly tough. The major challenges? Well, for one, as network conditions change minute by minute, systems have to dynamically reconfigure their transmission parameters, like constantly tweaking the modulation scheme to fix error rates on the fly. Secondly, as we push into 5G and start using way higher frequencies, we are fighting a relentless physical battle against path loss. Simply put, those high-frequency signals just naturally weaken a lot faster over shorter distances. And honestly, that brings us right to the bleeding edge of what's possible today. We have just built this entire stack, starting from basic electrical currents all the way up to global spectrum management. So I want to leave you with a thought to chew on. As our world demands even faster speeds and absolutely zero latency, how do you think evolving techniques like dynamic spectrum management are going to shape the limitless future of telecommunications? Keep that in the back of your mind as you prep for your exam. Remember, this is a massive, invisible architecture you're learning to control. Good luck with the studying, and thanks so much for joining me in this explainer.